Welcome to Talk Tensors. If you're tuning in, you probably know the feeling, that specific mix of excitement and total exhaustion when you realize the architecture you spent the last 6 months optimizing might have just been rendered obsolete by a paper that dropped this morning.
It's the constant treadmill of the field, isn't it?
It really is. We are your source for the deep technical analysis of machine learning and technology trends, where we don't just read the abstract, we try to debug the implementation.
And usually that means we're talking about making the existing machinery bigger. You know, scaling laws, quantization, new kinds of sparse attention. We're always talking about how to optimize the engine.
But today is different.
Today is very different.
Today we're talking about ripping the engine out entirely and replacing it with something that looks, frankly, a bit alien. We are doing a deep dive into Kolmogorov-Arnold Networks, or CANs.
And before you roll your eyes and think, great, another acronym to memorize, we should be really clear. This is not just a reshuffling of layers.
No. This challenges the fundamental atomic unit of deep learning itself.
It really does. I mean, for the last decade, maybe even longer, we have all been living in the era of the multi-layer perceptron, the ML.
It's the status quo.
Yeah.
It's the default Lego brick. You look at a transformer, you look at a CNN, a Mamba block. It doesn't matter what the hot new thing is.
Deep down at the bottom of the stack, it's all just MLTs.
Right. It's the bread and butter. And I think we have to start there because to really understand why Kankins are such a potentially violent disruption, you have to get what they're disrupting.
Absolutely. So an MLP, what are we talking about? It's a very, very specific recipe. Matrix multiplication followed by a nonlinearity.
That's it. That's the whole game.
Exactly. And in that standard view, the intelligence, if you want to even call it that, it all lives in the connections. You've got a layer of neurons and they're connected to the next layer by these, wires.
And each wire has a weight. Just a number.
Just a single scalar value, a floating point number.
So mechanically, I take my input vector, I multiply it by this huge matrix of weights. That's just the linear projection. And that tells me how loudly the signal should arrive at the next neuron.
Correct. And this is the most crucial part. The neuron itself is, relatively speaking, pretty dumb.
It's just an adder.
It just sums up all those incoming weighted signals, and then it applies a fixed function, a nonlinearity. Usually it's a ReLU or maybe a CU or a GLU if you're feeling fancy.
But those functions are static. A ReLU is always max, 0, x. It doesn't learn anything. It doesn't change its shape during training. It just sits there and clips all the negative values.
Precisely. So the entire MLP paradigm is what you'd call connection-centric. The complexity, the learning, it's all in the web of connections. The nodes are just simple gates.
Okay, so that's the world we live in. Now enter CANs.
Kolmogorov-Arnold Networks flip this completely on its head. They ask a really profound question. What if we remove the linear weights entirely?
Like, just get rid of them.
Get rid of them. And what if, instead, the edges themselves didn't just scale the signal, but actually transformed it?
This is the part that kind of breaks my brain a little bit. You're saying in a CAN, the edges don't have a weight. They have a function.
They have a learnable function.
So, okay, let me see if I've got this. Instead of a wire with a simple volume knob, every single connection between every single neuron is now a tiny, independent mathematical machine that takes a number in and spits a different number out based on some curve that it learns during training.
That is the shift. You've gone from connection-centric to what we're now calling transformation-centric computing.
Yeah.
In a CAN, the edges do all the heavy lifting.
And the nodes, what do they do?
The nodes just sit there and sum things up. They don't even have activation functions in the traditional sense. The activation is on the edge.
Okay, but hold on. I have to play the skeptic here right out of the gate. An MLP weight is one number.
Yeah.
A float 16, maybe even an innate 8 if we're quantizing. It's tiny. If you tell me that every single edge is now a function, that sounds massive. A function isn't one number. How do you even store a function on a wire? That sounds like a parameter nightmare.
That is the billion-dollar question, isn't it?
Right.
And it brings us right to the architecture. How do we parameterize a learnable one-dimensional function? And in the CAN implementation that's making all these waves, the one from Lou and his colleagues, they use B-splines.
B-splines, wow, okay. I haven't thought about those since my first computer graphics class.
It's the exact same math. It's the stuff used to draw smooth curves in vector illustration software like Adobe Illustrator or Figma. A B-spline or a basis spline is just a piecewise polynomial.
Okay, let's drill down into this because this feels like the core mechanic of the whole thing. When we say piecewise, we mean the curve is broken up into little segments, right?
Correct. Imagine your x-axis, that's your input range for the signal on that edge. You chop it up into a grid. Let's say you have 5 intervals on that grid. In each one of those 5 intervals, the function is defined by a specific, simple polynomial curve. The B in B-spline stands for basis. The final smooth curve you see is actually a weighted sum of these local basis functions.
So mechanically, on the GPU, instead of storing one weight per edge, we're now storing a set of coefficients. These are the control points that define the shape of this little squiggle on the edge.
Exactly. If you decide on a grid size of, say, 5, and you're using a spline of order 3, you might be storing, 8 or 9 coefficients for that one edge instead of just one weight.
That sounds incredibly inefficient. I mean, you're increasing the parameter count by nearly an order of magnitude for every single connection. Why on earth would we do this?
Because of one magical property, local control. This is the absolute superpower of the spline.
Right.
In an MLP, think about it. If you change a weight in that big matrix, you affect the output for every possible input that passes through that connection. It's a global change. If you tweak a weight to fix an error for an input of 5, you might accidentally break what the network learned for an input of Bedekin 5.
Right, that's just standard catastrophic interference. You're constantly fighting this battle of balancing gradients across your entire data set.
But with a B-spline, because it's piecewise, changing one of those control points only affects the curve in that specific local interval of the grid. If I grab a control point on the far right of the graph and I yank it up, the left side of the graph doesn't move at all. It's completely frozen.
I see. So the network can learn to fine-tune its behavior for a very specific range of inputs, say, when the signal is really high, without messing up what it already learned for when the signal is really low.
You got it. It grants the network a level of plasticity and precision that MLPs just structurally do not have. And this leads directly to the second major architectural feature, which is grid extension.
This was the part of the paper that genuinely impressed me. The idea that you can change the architecture of your model during the training process.
It's a bit like focusing a camera lens. When you start training a CAN, you don't need a super high-resolution complex function. You can start with a really coarse grid, maybe just 3 intervals. It's cheap to compute. The network just learns the rough overall shape of the function it needs. Maybe it learns, oh, this edge needs to look something like a parabola.
So you train cheap and fast at the beginning. Get the big picture right.
Right. But then later on, you realize you need higher precision. You need to capture the finer details. In an MLP, if you wanted more parameters, what would you do? You'd have to stop, add a new layer, or widen an existing one and restart the whole training from scratch.
Oh, a reset, yeah.
In a CAN, you can just extend the grid. You dynamically refine the mesh. You inject more control points into the spline.
But how do you initialize those new points? If you just stick them in randomly, wouldn't your loss function go crazy?
No, and this is the really clever part. You don't do it randomly. You use a least squares formulation to calculate exactly where the new control points should sit so that the new high-resolution curve perfectly matches the old low-resolution curve.
So the loss doesn't jump. The function's output is identical right after the extension.
The loss stays exactly the same. You've just increased the potential complexity of the model, the degrees of freedom, without breaking anything it already knows. Then you just continue training, and the network uses those new control points to learn the tiny, high-frequency details it couldn't before.
It's like sketching a drawing. You start with big, loose charcoal strokes to get the composition right, and then you switch to a fine point pen to do the detailed shading. You never erase the charcoal, you just refine on top of it.
That is a perfect analogy. MLPs are stuck using the same thick Sharpie marker for the entire process. KNs can switch pens mid-drawing.
Okay, so structurally, the data flow is input comes in, it passes through a learnable spline on an edge, it arrives at a node which just sums it up with everything else, and that sum is the output to the next layer. That's the KM layer.
Almost. There's one small but important implementation detail that really matters for stability in practice. Pure splines can be a bit finicky to train from a random initialization. Gradients can vanish or explode.
Of course they can.
So in practice, the authors use a residual connection.
Like in a ResNet,
Yeah.
a skip connection.
Similar concept. They basically include a standard linear activation path, usually involving the silo U function, that runs in parallel to the spline. So the signal actually goes through the spline and through a standard weighted connection, and the results are summed.
So it's like putting training wheels on the splines.
That's a great way to put it. Ideally, the simple silo U path handles the bulk of the signal flow early in training, which keeps things stable and allows the spline to slowly learn the more complex deviations and the nonlinear nuances without crashing the whole training run.
Got it. Okay, so that's the what of the architecture. But we really need to talk about the why. Because this didn't just come out of nowhere. This isn't just some hacker playing around with splines. This is based on a mathematical theorem that's, well, arguably one of the most important in the entire history of approximation theory.
The Kolmogorov-Arnold representation theorem from 1957.
1957. That is ancient in computer science terms. We were barely using transistors back then. The space race hadn't even really started.
Andrei Kolmogorov and his student Vladimir Arnold were absolute giants of mathematics. They were tackling one of Hilbert's 23 problems, specifically Hilbert's 13th problem. I won't bore you with the full history of all 23 problems, but the gist of this one was, can every complex multivariate function be broken down into simpler parts?
And the answer they came up with was yes.
The answer was a shocking, resounding yes. They proved that any continuous multivariate function, think of a function that takes 100 different inputs and tries to predict the weather, can be represented as a superposition, a sum of continuous functions of just one variable.
Let's just pause on that for a second. A superposition of functions of one variable. That means just simple 1D functions, lines on a 2D graph.
Exactly. The theorem basically says you don't need to learn complex, high-dimensional surfaces to model the world. You just need to add up enough simple 1D squiggles in the right way.
So if this theorem has been around since Eisenhower was president, and it essentially says MLPs are overkill, you just need a bunch of 1D functions, why aren't we all using this? Why did Hinton, LeCun, and Bengio build the entire deep learning revolution on matrix multiplication instead of this theorem?
Because the theorem in its original form came with a curse. It was a constructive proof, which means it showed that such functions exist, but the actual functions that Kolmogorov and Arnold used in their proof were nasty.
Nasty how? What does that mean?
Pathological. They were fractal-like. They were continuous, but nowhere differentiable. Highly, highly non-smooth. If you tried to plot one, it would look like TV static or just an infinitely jagged edge.
And you can't do gradient descent on a jagged edge? There's no slope?
You absolutely cannot. Modern AI is built on the foundation of backpropagation, which requires everything to be smooth and differentiable. You need a smooth slope to roll the optimization ball down. The original KA functions were a mathematical curiosity, but they were widely considered totally useless for any kind of practical engineering.
So the big innovation of the modern Kane paper isn't the theorem itself. It's the realization that we can cheat a little.
But that's it exactly. The authors of the recent paper said, okay, the original theorem uses these crazy fractal functions to guarantee representation with a very small fixed number of neurons. What if we relax that constraint?
They traded mathematical exactness for practical trainability.
Right. They said, let's use smooth B-splines. They're infinitely differentiable. They're nice to work with. And to compensate for the fact that they aren't as magically powerful as those fractal functions, we'll just add more of them. We'll make the network wider and deeper, just like we do with MLPs.
So they took a pure mathematical impossibility and turned it into a tractable engineering approximation.
And in doing so, they claim to have found a way to tackle the infamous curse of dimensionality.
The curse. This is a term we throw around a lot in the field. High-dimensional space is sparse and lonely, and so on. But specifically in this context, what does the curse mean for a standard MLP?
For an MLP, as the number of your input variables grows, as your dimensionality increases, the number of parameters you need to properly model that space typically grows exponentially. If you want to model a complex interaction between 100 different variables, a standard dense network needs to be absolutely massive to capture all those potential cross-correlations.
Because it's trying to approximate a very complex, curvy, high-dimensional surface, but just sticking together a bunch of flat planes, which is what real US fundamentally are.
Correct. But the argument for Kansas is that since they decompose everything into these 1D functions, the parameter count scales linearly, or at least much more gracefully than MLPs. They argue they can fit these high-dimensional functions with parameter count that grows much more slowly. Something like $1 versus those dollars in certain contexts.
And this is part of the white box promise, right? The idea that if the network is just a sum of a bunch of 1D functions, we can actually look at them. We can understand what it's doing.
Yes, and we will definitely get to the interpretability because that is really where CAMs seem to have an undisputed edge. But I have to stop you on that scaling claim because while the parameter count on paper might look efficient, the computational cost is a completely different story.
This is where we have to stop the hype train and look at the engine's temperature gauge.
Yeah.
Because every single implementation I've seen of CANs is slow.
Slow is being generous. We are seeing reports of training times that are 10x, 20x, sometimes even 100 times slower than an equivalent MLP doing the same task.
100 times slower. That makes it a complete non-starter for something like training a large language model. You just can't train GPT-5 if it's going to take 100 years instead of 1 year.
Exactly. And we need to be really clear about why it's so slow. This isn't just bad code or an unoptimized library. It is a fundamental mismatch with our current hardware.
We're talking about GPUs, NVIDIA H100s, A100s, all the hardware we've spent billions of dollars building.
Right. What is an H100 chip physically designed to do above all else?
Matrix multiplication. Dense, massive dot products as fast as possible.
It's a GMM, Machine General Matrix Multiply. The silicon is literally etched to take two giant blocks of numbers and smash them together in a single clock cycle. It relies on a principle called SIMD, single instruction, multiple data. Everyone does the same thing at the same time. They all march in lockstep.
And a spline doesn't march.
A spline meanders. It has to think. Think about the process of evaluating a B-spline. For every single input number that comes along an edge, the very first thing you have to do is ask, where am I?
You have to find which grid interval you fall into.
You have to find which interval, $2, TI plus 1, that it is a conditional check. It's an if-else statement. Or maybe a binary search if you're clever.
And GPUs famously hate if statements.
They absolutely despise them. It causes a phenomenon called warp divergence. If you have a warp of 32 threads running in parallel, and 16 of them need to look at the coefficients for interval A, and the other 16 need to look at interval B, the GPU has to serialize that execution. It pauses half the threads, runs the first batch, then it pauses the first batch and runs the second. You've just lost all your parallelism.
And on top of that, you have to fetch the right coefficients from memory. In a matrix multiply, the memory access pattern is totally predictable. It's a nice, clean, streaming read.
With a CAN, it's a scatter-gather operation. You're grabbing little bits of data, the coefficients, from all over memory, based on where that input value happened to fall in the grid. It completely thrashes the memory bandwidth, so you have high arithmetic intensity and poor memory locality. It is the absolute perfect storm for a slow C/A kernel.
So until NVIDIA decides to build a spline processing unit instead of a tensor processing unit, CANs are going to be fundamentally bottlenecked by the hardware.
Or until someone writes a truly god-tier custom C/A kernel that can somehow optimize this index lookup and memory access pattern. There is work being done. There's a repo called Efficient CAN that speeds this up significantly, but it's still fighting against the basic physics of the chip design.
Okay, so if they're slow and they eat VRAM for breakfast, why do we even care? What is the killer app that makes all this pain worthwhile?
The killer app is science, specifically a field called symbolic regression.
And this goes right back to that white box idea we mentioned.
Yes. Let's say you're a physicist, you have some data from a particle collider or maybe a fluid dynamics simulation. You don't just want a black box that can predict the next frame of the simulation. You want the equation. You want to discover the underlying physical law.
You want to find the EM2CF2 in your data.
Precisely. With an MLP, you can never ever get EMC22. You get a matrix with 10 billion floating point numbers that together approximates the behavior of EMC22. But with a CAN, because the edges are actual plottable univariate functions, you can just look at them.
So you train a CAN on your physics data. After training, you can open up the hood of the network and look at, say, edge number 4.
And you plot it. And you see a perfect sine wave. It looks exactly like a sine wave. So you go to the computer and say, okay, replace this complicated spline on this edge with the simple symbolic function somewhere. Then you look at the next edge. It looks just like a quadratic curve, like 6 pi 2 thalers. So you replace it.
You're pruning the neural network back into clean, human-readable mathematics.
You are distilling the entire neural network into a compact symbolic equation. The original paper demonstrates this beautifully. They rediscovered known physical laws from synthetic data by just training a CAN and then reading the functions right off the edges.
That is profound. It's an AI that can explain itself in the universal language of mathematics.
And it's also incredibly data efficient. This is the other big win that's often overlooked. CANs might be slow to train per step, but they often require far fewer data points to learn the underlying law. If you're trying to discover a new law of nature, you don't always have big data. You might only have a few hundred precious experimental observations. CANs can maximize the utility of that small data because they're searching for structural patterns, the shape of the spline, rather than just brute force statistical correlation.
So the takeaway here is, if I'm building a chatbot to summarize my emails, I should stick to MLPs. But if I'm trying to figure out the governing equations of a new room temperature superconductor from my lab data, I should be looking very seriously at cans.
That is the current consensus, absolutely. Scientific machine learning, or CML, is the clear beachhead for this entire architecture.
But there's a catch with the learning part too, isn't there? We have to talk about catastrophic forgetting.
Yes, the bane of any kind of continual learning system.
Just to remind everyone, catastrophic forgetting is that classic problem where a network learns task A perfectly, then you train it on task B, and in the process, it completely erases task A from its brain.
It's because the weights in an MLP are global resources. To learn the new task, you perform gradient descent, which shifts the entire weight matrix. It's like trying to learn how to play the piano, and in doing so, you accidentally rewrite the part of your brain that knows how to walk.
Initially, when cans came out, I saw a lot of people arguing that they would just solve this problem out of the box because of that local control property of splines we talked about earlier.
The theory was very sound. If task A only uses the input range $0, $1, and task B only uses the input range $2, $33, then in theory, the splines should update in completely different places. The control points for task A should never be touched by the gradients from task B.
Perfect separation. Zero forgetting. Problem solved.
In a perfect synthetic world, yes. But the real world is messy. Real-world data distributions overlap. If you're doing image recognition, the pixel values for an image of a cat and an image of a dog are in the same numerical range, from 0 to 255.
We call this spline input overlap.
Right. So when you train on dog images, you are inevitably wiggling the very same control points that you just used to learn cat images. And because splines are so incredibly flexible, they're so wiggly, they can change their shape radically with just a few updates. Early tests actually showed that unmodified cans were worse at catastrophic forgetting than MLPs. They were so plastic, they would just rewrite themselves instantly.
But there is a fix for this. I was reading about a new method called WiseCan.
WiseCan, I love the name. It stands for Wavelet Integral Spline. No, I'm just kidding. It just implies that it's a wiser way of doing things.
It implies managing your memory and your resources properly.
Exactly. WiseCan introduces a set of strict rules for how the spline coefficients can be used and updated. It treats the network's capacity as a finite resource that has to be carefully allotted over time.
So what are the rules? What does it do?
Rule number 1 is parameter isolation. It programmatically assigns specific basis coefficients to specific tasks. Rule 2 is the big one, the freezing rule. Once a coefficient has been trained for task A, it is locked. It's frozen. Gradients from future tasks cannot touch it.
So it's like writing in pen. Once that part of the function is learned, you can't erase it.
But here is the key, and this is what makes it work, the visibility rule. Future tasks can still see the old frozen parameters. They can use the frozen part of the spline to calculate their forward pass. They just can't update them.
Oh, that's very smart. So if I learned how to recognize a curve shape for task A, task B can come along and say, hey, I need a curve just like that one. I'll reuse the function you already built, but it's not allowed to distort it in the process.
It forces the network to build on top of its previous knowledge, rather than just overwriting it. It's a constructive, cumulative approach to learning. And when they run out of fresh coefficients in a particular grid, they just use that grid extension trick we talked about to add more fresh coefficients for the new task to use.
So the network literally grows as it learned more tasks. It physically, or at least virtually, expands its capacity to accommodate new knowledge.
And they combine this with aggressive pruning. If a coefficient isn't doing anything useful after a while, they just delete it. It keeps the memory footprint from ballooning. And the results are impressive. WiseCan significantly outperforms both standard MLPs and standard cans in these sequential continual learning benchmarks. It really suggests that this kind of architecture might be the key to building lifelong learning agents AIs that can operate for years and years without needing a full reset.
That feels so much more biological. My brain doesn't just format its hard drive every night. Well, usually.
Depends on the weekend, I suppose.
A fair point. Okay, so we've got the basic architecture, the deep theory, the speed bottleneck, and now a potential solution to forgetting. But the field isn't standing still. The main paper dropped, and then the GitHub repos just exploded. We're now in the middle of a zoo of CAN variants.
It's the Cambrian explosion of learnable activation functions. People very quickly realized that B-splines are not the only game in town, and maybe not even the best one for every problem.
Let's talk about some of the big ones that are getting traction. WiseCan.
Wavelet can. This is my personal favorite, especially for anything involving signal processing.
Wavelets. Those are the little mathematical packets we use to compress JPEGs and MP3s, right?
And MRI scans, yeah. A B-spline, as we said, is localized in space, meaning the input value range. A Fourier transform is localized in frequency. A wavelet is clever because it's localized in both space and frequency. It's like a little packet of a wave that exists for just a short time and at a specific scale.
So why would you want to put that on the edge of a neural network?
Because so much real-world data is non-stationary. It has sharp spikes, transients, and glitches. A B-spline can struggle to capture a really sharp spike unless you have a ton of grid points right there. A wavelet, by its very nature, is designed to capture high-frequency details efficiently. As a result, WaveCans often train significantly faster than the standard B-spline cans because the wavelet transform is just a more efficient basis for many kinds of data.
Yeah, that makes sense. And then on the other end of the spectrum, there's Chebyshev.
Chebyshev polynomials. This is one for the math purists and the CNML folks. Chebyshev polynomials are orthogonal. That's a fancy way of saying they don't overlap in the information they represent. They are incredibly stable for approximating very smooth functions.
So if I'm doing that physics discovery stuff we talked about, solving PDEs and whatnot, yeah. Chebyshev is probably a better choice than the standard can.
Almost certainly. It avoids a nasty numerical issue called the runge phenomenon, where high-order polynomials can start oscillating wildly at the edges of an interval. Chebyshev stay smooth and well-behaved, which is exactly what you want when you're modeling the laws of physics.
And what about for the people who are impatient? The people who hear 100x slower and just want a version that runs fast? The cheaters.
For them, there is ReallyCan.
Is it really a can if it uses ReallyUse? That feels like a philosophical question.
Philosophically, maybe not. But architecturally, it's a very clever hybrid. It uses the core basis idea of cans, summing up a bunch of simple functions, but instead of a complex spline calculation, it just sums up a bunch of shifted and scaled RealUs. And since RealUs are just simple matrix linear operation plus a threshold, it can run at nearly MLP speeds on modern GPUs.
So you get some of the learnable edge function benefit, or at least an approximation of it, without paying that massive warp divergence penalty.
Exactly. It's the pragmatic engineering choice for when you want some of the can flexibility but can't afford the performance hit.
It really feels like we are unbundling the concept of the neuron. For 50 years, the neuron has been this monolithic concept. Now we're breaking it apart and asking, what kind of specific math do you want to happen on this particular wire?
That is the emerging choose your can paradigm. We're moving toward these bespoke hybrid architectures. You might imagine a future model that has a logic can layer for reasoning, followed by a Fourier can layer to handle periodic data, all wrapped inside a larger transformer block.
Which brings us to the big so what. We have listeners who are running R&D teams, listeners building startups, PhD students trying to figure out what to work on. What is the practical takeaway? Are cans going to replace MLPs?
Not today, and probably not for what we call general purpose compute, like powering LLMs in the next 12 to 18 months. The hardware headwinds are just too strong right now. But for specialized tasks, they are a game changer. For interpretability, for scientific discovery, for control systems, for robotics, and for any data-sparse environment where you need to squeeze every drop of insight from your data, they are already proving to be superior. If you need to know why your AI made a decision, cans offer a direct path to an answer that MLPs simply cannot provide.
It's a tool for precision and interpretability, not just for raw scale.
That's the perfect way to summarize it.
All right, this brings us to my favorite part of the deep dive. Novel notions. This is the segment where we take the technology we've just spent an hour dissecting, we throw away the peer review process, and we speculate wildly on where this could all be heading.
And the usual disclaimer applies. The following ideas are for entertainment purposes only. Please do not go and invest your life savings based on our sci-fi ramblings.
Unless it works, in which case you heard it here first.
Okay.
Novel notion number 1, the self-discovering physics engine.
I absolutely love this concept. Think about any modern video game engine like Unreal or Unity, or think about a simulation environment for training robots like MuJoCo. Right now, the physics in those engines are hard-coded. A human programmer wrote the equation for gravity. Someone else wrote the code for friction and collisions.
And complex, soft body physics, things like water simulation or mud or cloth, that stuff is incredibly computationally expensive because the underlying equations are total nightmares to solve.
Exactly. Now imagine a new kind of engine that runs on a can. It doesn't have any of those equations pre-written. It starts with a blank slate. It just observes objects interacting in its world. It sees a ball bounce a few times.
And it runs that symbolic regression loop we talked about in real time. It fits a spline to the trajectory of the bounce. It looks at the spline and realizes, oh, that's just a parabolic arc with a simple damping coefficient.
It literally writes its own physics code as it runs. It replaces the expensive general-purpose mesh collision detection with a simple, fast mathematical function that perfectly predicts the position of that specific ball.
So the longer you play the game or run the simulation, the faster it gets.
Yes. The engine continuously optimizes itself by learning the laws of its own universe. A neural physics engine that doesn't just approximate physics, but discovers and implements the most computationally efficient mathematical representation of it on the fly.
That would be unbelievable for things like VR and the metaverse. You could have hyper-realistic complex interactions that become computationally cheap just by virtue of you interacting with them.
Notion number 2. The analog CAN chip.
Okay, so we talked at length about how digital GPUs with their matrix multiply cores absolutely hate running CANs. But nature loves continuous functions.
Light is a wave. It is a continuous function. A gravitational field is a continuous function. Why are we simulating these beautiful, smooth curves with billions of discrete, clunky digital steps on a silicon chip?
You're talking about an optical computer?
An optical CAN. Imagine a new kind of chip where the spline function on an edge isn't a lookup table of coefficients stored in VRAM. Imagine it's a physical material, a liquid crystal, or a phase change material that literally modulates a beam of light as it passes through it.
So the function is embodied in the physical shape and properties of the medium itself.
Precisely. You shine a laser, which is your input signal. The material physically bends the light, which is the spline function being applied. And to perform the summation at the node, you just use lenses to focus all the light beams onto a single optical sensor. Physics does the addition for you instantly.
No warp divergence, no memory bandwidth bottleneck.
Just the speed of light. This could be the architecture that finally makes analog computing a mainstream reality, because CANs map one-to-one to physical transformations in a way that abstract matrix multiplication really doesn't.
That's the true neuromorphic dream right there. Okay, notion number 3. Let's bring it back to Earth a bit. The juror's AI.
This one is about the societal application.
We have this massive growing problem of black box AI being used in high-stakes domains like law, medicine, and lending. You can't put a traditional neural network on the witness stand and cross-examine it.
You ask it, why did you deny this person a loan? And the answer is because the output of neuron 7,342 was 0.7. That's not a reason. That's not an explanation.
But with a CAN, we have the graphs. We have those interpretable 1D functions on the edges.
So imagine a future juror's AI system used for making critical decisions like parole or credit scoring, where the architecture is legally mandated to be a CAN. When a decision is challenged or audited, the system doesn't just produce a log file, it produces the audit trail.
Not a trail of logs, a trail of graphs.
You can literally plot the function on the edge that connects the input zip code to the output risk score. If that graph shows a sharp, unfair spike for a specific zip code, a human auditor can point directly to it and say, that is redlining, that is demonstrable bias right there in that function.
And here's the real kicker. You can then fix it manually.
You can open up the equivalent of a spline editor, grab that one control point causing the bias, and drag it down. You can surgically intervene and force the AI to be fair by literally flattening the discriminatory curve. You can't do that with an MLP's weight matrix. You can't just edit one weight out of a billion and expect to remove bias without retraining the whole thing and just hoping for the best.
Interpretable, editable, and auditable AI. That might be the only way we ever get regulators to sign off on fully autonomous systems in critical public infrastructure.
It bridges the gap between the raw statistical pasture of modern AI and the fundamental reasoning requirements of the law and ethics.
Well, on that rather profound note, I think my brain has been successfully transformed from a scalar value into a complex spline.
A high-order polynomial, I certainly hope.
We'll see how well I generalize to the next topic. This has been a very deep dive into Kolmogorov-Arnold networks. They're complex, they're currently slow, but they're absolutely fascinating. And they might just be the future of scientific discovery and explainable AI.
If you want to dig deeper and play around with this yourself, check out the PyCan repository on GitHub and look up the WiseCan paper for the continual learning aspects. The code is out there.
Until next time, keep your gradients flowing and your tensors talking.